Hello and welcome, my dear students. Here we will now discuss about inverse DFT, that is discrete Fourier transformation. What is discrete Fourier transformation? We have learned from the previous lectures, but now it's a time to find out the basic thing of the sampling, the sample values right there. The inverse transform follows the DT Fourier series. What is the inverse DFT? So in previous lectures, that is the only thing we have to find out, that is the point xk, that is the Fourier transform, right? We have to make it inverse to find out the xn, that means the original value, the input values, the value that is determined on the discrete time series. So when we will go through to it, the equation will be 1 by n, k equal to 0, n minus 1. That is the important thing. In the previous equation, we have seen one thing. How can you remember this? Okay, just go and just remember this thing. Okay, so that's the thing. Okay, here you can see there is no 1 by n here. Okay, that's the, just see this. That's the limited. It's not, it's unlimited, it's limited. Here you can see xk n equal to 0, n minus 1, xn e to the power minus j twice pi k n divided by n, right? The minus power will be now plus, the additional 1 by n will be multiplied there, and the smaller n will be replaced by k, and the xn will be replaced by the x to the power x of e to the power j omega. I apologize for the mistakes. Okay, now go through the inverse DFT. As I have told you before, 1 by n comes there, k with yielding the n, and xk is the sequence of the inverse, sequence of the sequence of the DFT of a signal, and there is no minus here. All things are similar to it. Okay, so there is an inverse discrete Fourier transform, as you can say, MATLAB code, the MATLAB code. So it is also dependent on this and is governed by this equation. That's it. And you have to just define a function, that is IDFT. The function has been defined here. So go through to the next slide. So there is a computational method of finding the inverse DFT, inverse discrete Fourier transformation. Okay, let us find out from the previous math. Whenever we turn out the 1 2 to 1 sequence to the xk with 6 minus 1 minus j, 0 minus 1 plus j, for k equal to 0, 1, 2, 3 values, right? So when you just transfer this, now again you got this value on the mathematics part of your question or any kind of math problem. They want you to compute the inverse DFT to find out the inputs, right? Input sequences. So get the xk here. So there are 4 points. Okay, first of all, come along with the n equal to 4. Okay, that will be 1 by 4, right? x0, x1, x2, x3, that means 0 to 3, n minus 1. This equation is going along, and also there is a summation equation. Okay, and each and every part, when you find out this 1, 2, 3 has been calculated, which part is changed here? The part of k, not the part of n. In previously DFT you have to change the part of n, the part of index. Now you are find out the indexes. Okay, the value, the previous values. So just put the value here and get the value there. After that you put the value through 0 to 3 on the n values to find out the real value of the previous sequences. Okay, just put the value x equal to 0, put the value in this equation. That's the finalized equation. Take about with 1, just put the value n equal to 0 in each of the part. E to the power 0 will come along to the 1, and you know what is x0 value, it is 6. What is x1 value? -1 minus j. What is x2 value? 0. What is x3 value? -1 plus j. Okay, put it out. You will get this. That is the value of 1. That is the value of this first sequence 1. Go through to the second part, that is x1. 1 by 4. Similar situation. Put the value n equal to 1 here. After calculation, you will get it out. You will get it out. You will get the value 2. Again, the same thing repeats, and for it repeats throughout until you get the final destination of x3, right? Okay, that's the thing of computation of the inverse DFT. Now get on to the next slide to make it a finalized situations. So what is the relationship to the DTFT? So there is a very narrow sequence between DTFT and DFT, a very narrow relationship. Okay, there's the relationship of interpolation. What is interpolation? Okay, let us discuss about interpolation. So the DFT and the DFT are related by this. So that's not the DFT, right? That's the DFT and IDFT maybe. So that's the DFT, and exact DFT is that, as we can find out the equation in the previous lectures. So if we define a pulse here, xn, so that's the pulse sequence as you can see here, and there is a value of q. What does the value of q do? Okay, just make a simple value q that will change the entire DFT sequence. Okay, we will just take to make it DFT. Okay, x e to the power j omega, the omega sine, that is the sinc function, as you can see, sine theta divided by the, that means sine theta plus something divided by sine theta, whatever else it might be, e to the power minus j q omega. Okay, all things are correct. You put the value there, just put the value q5 and n into 22. That means the slicing value, that means here you can see slicing value, that means the lobe width has been changed, the sample has been taken at 22. You will get this. If the sample increased 88, you will get many smaller sequences come along together and very much similar to the previous, what can you say, previous graph, whether the input is. So the DFT is simply a sampling of the DTFT equispaced points along the frequency axis. That is the DFT. It is sampling, simple sampling. But DTFT, as n increases, the sampling becomes finer. Note that this is true even when q is constant. The q is constant here, q haven't changed, but the n number of samples has been changed. True even when q is constant. Increasing n is a way of interpolating the spectrum. So that is the interpolation. Whenever you increase the number of samples, it will converges and it will be pretty much closer to the previous sequence or previous graph. So that is the basic theme of interpolation. So that is the similarity or relationship between DTFT and DFT. Okay, so there are some DFT of truncated signals, how the signals can be truncated. That's the hint of convolutions are there. What if the signal is not time limited? Here you can see there are some other windows, popular windows. We will know about windows in the later part of the lectures. What are the windows? What is the basic of the windows? What are rectangular, general Hamming, triangular, Chebyshev filters? A lot of things waiting for us. Thank you very much for being with me.